We'll continue the conversation of induction motor theory and operation with the topic of power and torque in the induction motor. If we consider one phase of the motor, we can describe the input current to that phase as follows. So here the voltage, or the current flowing into one phase, is the phase voltage divided by the equivalent impedance, and we'll write an expression for the equivalent impedance, which would be R1 plus JX1 plus, this all comes from the equivalent circuit, 1 over G sub C minus J B sub M, this is the contribution of the magnetization portion of the circuit, plus, from our secondary side, 1 over R2 over S plus JX2. We can express the copper loss in the stator portion of the circuit, which we will call PSCL for stator copper loss, and this would be 3 I1 squared R1. Now the reason why it's 3 times I1 squared R1 is because we're considering the loss in 3 phases. So I1 describes the current in one phase of the circuit, R1 the associated resistance. We're of course assuming that the 3 phases are identical, so the currents will be identical because the resistances are identical, so we get a total stator copper loss in the stator of 3 I1 squared R1. The core loss let's say P core equal to 3 E1 squared G sub C. And so now we can write an expression for the power in the air gap. This is the gap between the stator and the rotor. So we will express this P AG, and this would be equal to the input power minus the stator copper losses minus the core losses. That's how much power makes it into the air gap. Now, if you look at your equivalent circuit, you see now we're on the secondary side of the equivalent circuit. On the secondary side, the only element where this power can be consumed is the resistor with the value R2 over S. Okay, so once the power is on the secondary side, we have an inductor, which isn't going to consume any power, and we have a resistor. That's the only place where the power can be consumed. So So therefore, the power in the air gap can also be expressed as 3 I2 squared. I2 is the current flowing in the secondary side, or the rotor, times R2 over S. Remember, S here is the slip. When we refer the losses across the ideal transformer in the equivalent circuit, they're unchanged. Remember, power is not changed when we refer it across an equivalent ideal transformer circuit. So let's just say, since power is unchanged when referred across the ideal transformer, our rotor copper losses would be equal to 3 I2 squared R2. And the remaining power has to be the converted power. So we have our air gap power, which can only be consumed in R2. We have our rotor copper losses, and whatever remains must be converted into mechanical energy. So we write an expression for the converted power, which would be the air gap power minus the rotor copper losses and that equals 3 I2 squared R2 over S minus 3 I2 squared R2. And we can rearrange this equation. As such, and further in its final form, like so. Note that the rotor copper losses are equal to the air gap power times the slip. Or I'll write this more formally, the power in the rotor copper losses is equal to S times the air gap power. Therefore, the lower the slip, the lower the rotor loss in the machine. Also, if the machine is not turning, then the slip equals 1, and all the power is completely consumed in the rotor because there would be no converted power. And if we write, finally, the output power, P out, would be equal to the converted power minus some losses, friction and windage, and then any other miscellaneous losses. The induced torque is the torque generated by the internal electrical to mechanical energy conversion, and it differs from the available torque because of the losses of friction and windage, as well as the miscellaneous losses. So if we think about induced torque, we have our induced torque, which is the converted power over omega m, and we can rearrange this equation. One minus s times the air gap power, 1 minus s times the synchronous speed. Therefore, the induced torque is equal to the air gap power divided by the synchronous speed. So if we know the air gap power, we can find the induced torque. Now, part of the power coming across the air gap is consumed in rotor copper losses, and then the rest is converted to mechanical power. And we can separate these two in the equivalent circuit. Okay, so let's go ahead and draw the equivalent circuit. Now what I'm going to do is we're going to call this R2. This is where the rotor copper loss is going to come in. And then this resistor will be R2 times 1 minus S over S, and this is where the converted power is consumed. So the rotor copper losses are consumed in R2, and the difference between them is the converted power, which must be consumed in the second resistor. So converted power equal to R2 over S minus, or let's call this R converted, equal to R2 over S minus R2, which equals R2 times the quantity 1 over S minus 1, which equals R2 times the quantity 1 minus S over S. Hence, that value up there. Okay. So that's a summary of how the power flows through the induction motor. Next, let's talk about the torque speed characteristic. So consider if we had a squirrel cage induction motor operating at no load. So if it's operating at no load, that means it would be spinning very near the synchronous speed. And let's just draw a little depiction here of what's happening. Here's our induction motor. And it's going to be rotating at some speed omega. We have our stator field, B sub s, and then we have B sub r, our rotor field, and the vector sum of the two is B net. Now, if we think about the values of the different variables at play here, we can think B net, if we think of the equivalent circuit, B net is going to be proportional to E1. So if we consider E1 to be constant, then the net magnetic field will also be constant. Now, in reality, E1 is not constant. It varies as the load changes. And this is because R1 and X1 will cause varying voltage drops with different loads. But these voltage drops, these changes in voltage drop are relatively small. So for this analysis, we're going to consider that E1 is constant. And that assumption will allow this analysis to proceed. So, at no load, the value of the slip is small. Very little slip. And the relative motion between the stator and the rotor magnetic fields is also small. We said at no load we're going to be rotating very close to synchronous speed. Synchronous speed, of course, is the speed that the stator magnetic field is rotating, and if the rotor is turning very close to synchronous speed, then the relative motion between these two magnetic fields is going to be small. For that reason, we know that the rotor frequency is small. And due to this low frequency, then, the reactance of the rotor is also small. Therefore, the rotor produces a small magnetic field, B sub r, that's going to be a little bit more than 90 degrees behind B net because of the very small reactance. And then we can write an expression for the induced torque. K times BR cross B net. And if we think about the magnitude of this expression, it will be K, BR, B net, magnitudes again, sine delta, where delta is the angle between BR and B net. Since the rotor magnetic field is small, the induced torque is also small, and in fact it's going to be just enough to overcome the rotational losses, the losses due to friction and windage, and any other rotational losses. Okay, so that's the situation with the motor operating under no load. Now suppose we load the motor. Well, let's draw a picture of the situation with the motor loaded. We have our induction motor, and now we have our stator magnetic field, rotor magnetic field, the net, and we can think about ER and IR. Okay, so when we load the motor, the slip will increase, and the rotor speed goes down, as we would expect if we put a load on the motor. When the speed goes down, there turns out to be more relative motion between the rotor and the stator magnetic fields. remember B sub s rotating at the synchronous speed still, but B sub r is rotating at the rotor mechanical speed, which is now smaller because of the load, so there's more relative motion between B sub r and B sub s. Therefore, ER gets larger. ER goes up, and if ER goes up, then IR will go up. And if IR goes up, BR goes up. So more voltage is induced onto the rotor. More voltage on the rotor means more current flowing in the rotor. More current flowing in the rotor means that the rotor magnetic field will get larger. The angle of IR and BR also will change. Since we have a larger slip, the rotor frequency is going to increase, and that means that the rotor reactance increases, so the current in the rotor will lag further behind the motor voltage. So our slip is increased. This means that the rotor frequency will also increase. When the rotor frequency increases, the reactance associated with the inductor increases. Because it's a function of frequency. And since the reactance increases, the current in the rotor will lag further behind the rotor voltage. Now this increase in B sub r will will have the effect of increasing the torque. But the increase in delta, the angle between B sub r and B sub s, tends to decrease the torque. So the result is we have a net increase in torque to supply the increased load, but only up to a point. So we have two factors at play here. First of all, B sub r, the increase in B sub r, that tends to increase the torque. Let's just go back to the torque equation for a second. Okay, let's look at this one. So our induced torque is proportional to B sub r, and B sub r is going up. Okay, so that would tend to make the induced torque go up. But we also have this sine delta term here. Okay, and that angle delta is also changing. We've said that angle is going to change. So the increase in delta tends to decrease torque. So the net result as we put the load onto the motor, we increase the torque. As this load continues to increase, we reach a point where the sine delta term decreases more than the b sub r term increases. At this point, the sine delta term begins to dominate the torque equation, and the torque comes down. Now, this point where we reach this top of the torque curve is called the pull-out torque. When we reach the pull-out torque, any further increase in load will cause the motor to stop. Let's look a little bit more closely at the induced torque equation. We have torque induced equals K, which is motor constant, B sub R, B net, sine of delta. B sub R is directly proportional to the rotor current as long as the rotor is not saturated, which increases with increasing slip. So it's proportional to the rotor current and increases when the slip increases. So if we draw a plot, where this is speed on this axis and we have the synchronous speed, then we're going to have something like this. B net is proportional to E1. Now we've assumed in this analysis that E1 is constant. So B net is assumed to be approximately constant. Sine delta. Let's think about this sine delta term. Delta is the angle between B net and BR, and note delta is equal to the power factor angle plus 90. 90 degrees. So, sine delta is equal to the sine of theta r plus 90 degrees, which is equal to the cosine of theta r, which is the power factor of the motor. Theta r is equal to the inverse tangent of x sub r over r sub r, which is equal to the inverse tangent of s x r0 divided by r sub r. So if we plot the cosine of theta r, which is the same as the sine of delta, in terms of speed, it's going to look like this. Somewhere out here is the synchronous speed, and this axis is speed. And if we took these three plots and we multiply them together, we would get the torque speed characteristic, which looks like this. We have our synchronous speed. We plot induced torque. And that's what the plot is going to look like. Up here, at this point, we have our pull-out torque. So graphically, that's how we can think about this induced torque. We can derive the induced torque equation as well. So the induced torque is equal to the converted power divided by the speed, which we've shown is equal to the air gap power divided by the synchronous speed. Now let me just repeat the per phase equivalent circuit here. Slightly simplified version. We have JX1, R1. This is going to be JXM. E1 here. JX2 and the resistor R2 over S. Here's our phase voltage, and we have I1 flowing in this direction and I2 here. So if we refer to the circuit, the air gap power for one phase, we can write that expression. Air gap power, one phase, is equal to I2 squared R2 over S. You can think about the air gap as being in this vicinity. So once we get to this point where we measure the voltage E1, we've crossed the air gap. So the total air gap power for all three phases is equal to 3 I2 squared R2 over S. So this means if we can determine I2, we can determine the air gap power and the induced torque. So in order to find I2, we'll take the Thevenin equivalent of the portion of the circuit to the left of the X's where I indicate E1. Now recall, in order to find the Thevenin equivalent, we find the open circuit voltage at the point where we want to find the equivalent circuit. We short out the voltage sources. In this case it would be the V sub phi, the phase voltage, and we find the equivalent impedance looking into those terminals. And if I do that, well, once we do that, let's say, we find the Thevenin voltage. So keep in mind the Thevenin voltage is equal to, in this case it would be V phi Zm over Zm plus C1, and this is equal to V phi times JXM over R1 plus JX1 plus JXM. The magnitude of the Thevenin voltage is simply V phi times JXM divided by, times XM, divided by the square root of R1 squared plus X1 plus XM, that quantity squared. So I get the following. We have V phi call this Vt, and this is JX1, R1, JXM. Okay, Vt is our Thevenin voltage. In order to find our Thevenin impedance, we're going to short out V phi, so let's just redraw the circuit. Here we're finding the Thevenin impedance, and the circuit that we're concerned with there, of course we short out V phi, so we have JX1 and R1, JXM, and here are the terminals. So we find the impedance looking into this circuit is the Thevenin impedance, and this would be JXM R1 plus JX1 divided by R1 plus JX1. Let's just say J times the quantity X1 plus XM. So now we know the Thevenin voltage. We can redraw the circuit. So the result we have our Thevenin voltage Thevenin resistance, Thevenin reactance. This is where we were measuring E1, and then we have the right-hand side of the circuit, which is the inductor with JX2 and the resistor R2 over S. Okay, so what have we done? Let's just go back and look real quick. We started out with this circuit. We're looking to find I2. So in order to find I2, we took the Thevenin equivalent of everything from here over to the left. And we came up with this circuit, where we have now these Thevenin values. And now it's very easy to find I2. Remember, I2 is the current flowing here. We need to find the value for VTH. We're going to make some assumptions about VTH. Since XM is going to be much larger than X1, and XM is going to be much larger than R1, okay, looking back at this circuit here, we can say that the Thevenin voltage is approximately equal to V phi times XM over X1 plus XM. Since XM, again, is much greater than X1, and since XM plus X1 is much greater than R, we can create this equivalent expression for the Thevenin resistance, which is approximately equal to R1 times the quantity XM over X1 plus XM squared. Also, because of these assumptions, we can say that the Thevenin reactance XTH is approximately equal to X1. And now we can write a very simple expression for I2. I2 is equal to VTH divided by ZTH plus Z2. We can expand upon this. This is equal to VTH, using the expressions we just developed, RTH plus R2 over S plus JXTH plus JX2 we can find the magnitude of I2. Square root of the quantity R1 plus R2 over S squared plus the quantity XTH plus X2 squared. So the air gap power is given by the following expression. Remember, air gap power is equal to 3 I2 squared R2 over S. So this equals 3 VTH squared R2 over S divided by RTH plus R2 over S, that quantity squared, plus the quantity XTH plus X2 quantity squared. The induced torque is equal to the air gap power over the synchronous speed. So now we can write an expression for the induced torque, which would be as follows. 3 VTH squared R2 over S divided by the synchronous speed times the expression from the denominator of our air gap power equation, RTH R2 over S squared plus XTH X2 quantity squared. Okay. And this equation leads to the torque speed characteristic curve that we derived graphically before. So here's what it would look like again if we plotted it. And we're going to plot it. Here's our induced torque, and what we're going to do on the vertical axis here is this will be expressed as a percentage of the full load torque. So here is the full load torque. This is speed. And out here somewhere we have the synchronous speed. And we're going to get something like this. So this point here is the starting torque. When the speed is 0, that's the torque that we get. This maximum, again, is the pull-out torque. Beyond the pull-out torque, the motor is going to stop, and then we see that we produce 0 torque at the synchronous speed. So there's some things that we can note about this graph. At the synchronous speed, the induced torque is 0. That's what we expected. We have a linear region. The curve is nearly linear from the no load point to the full load point. There's a maximum torque that we can't exceed. The starting torque is larger than the full load torque. Okay, this is important because that means that carrying any load up to the rated load, we can start the motor simply by applying the power. We don't need any special starting circuitry, generally speaking, with induction motors. For a given slip, the torque rises as the square of the applied voltage, and we can use this idea to do some speed control. If the motor is driven faster than the synchronous speed, the induced torque reverses, and then the machine becomes a generator. Finally, if the motor is turning backwards relative to the direction of the magnetic fields, the induced torque will stop the machine rapidly. And so switching any two stator phases could be used to quickly stop an induction motor. So those are some things that we can observe by looking at this graph in the equations. Now, let's derive an expression for the maximum torque. Which, of course, we're calling the pull-out torque. Okay, well, let's just start with the idea that torque, again, is equal to the air gap power divided by the synchronous speed. So the maximum torque, so the synchronous speed is constant, so then we can say the maximum torque must occur when the air gap power is at its maximum. Now remember that the air gap power is equal to the power consumed in the resistor R2 over S. So when that power, the power consumed in that resistor is a maximum, that's when the air gap power is a maximum. So let's just back up and see what we know so far. The air gap power is the power consumed in R2 over S, and when the air gap power reaches its max, that's when the torque is going to reach its max. So let's look at this circuit. If we go back to using that Thevenin Equivalent circuit, we have our Thevenin resistance, Thevenin reactance, X2 on the rotor side, and then R2 over S. Now, recall that maximum power transfer occurs when the load impedance magnitude equals the source impedance magnitude. Okay, that's when we get maximum power transfer in any circuit whatsoever. Okay, that's why, for example, you match the impedance of a speaker to the impedance of the amplifier so that you get maximum power out of the amplifier into the speaker. Otherwise, power gets reflected back. Same concept here. We want the load impedance magnitude to equal the source impedance magnitude in order to get maximum power transfer. So, the equivalent source impedance Z source is equal to RTH plus J XTH plus J X2, right? Everything, here's our load is across R2 over S, so everything else is the source. Therefore, the maximum power is going to occur when R2 over S is equal to the magnitude of Z source, which is the square root of RTH squared plus quantity XTH plus X2 squared. Let's solve this equation for the slip. If we do that, we get the following. What we will call S max, this is the slip at which max power occurs, is equal to R2 divided by the square root RTH squared plus quantity XTH plus X2 squared. Notice that the slip of the rotor at maximum torque is directly proportional to the rotor resistance. And recall that the induced torque is equal to 3 VTH squared R2 over S divided by the synchronous speed. This is the equation we derived before. Oh, let me write it this way. If we insert this expression for maximum slip into this induced torque expression, we get the following. Maximum torque is equal to 3 VTH squared divided by 2 times the synchronous speed times RTH plus the square root of RTH squared plus XTH plus X2 quantity squared. And that was accomplished by substituting this expression in for the slip at maximum torque, giving us an expression for maximum torque. Note that the slip where maximum torque occurs is directly proportional to the rotor resistance. And on a wound rotor induction motor, we can bring the rotor circuit out to the stator by using slip rings. So this means that we can access the rotor windings on a wound rotor. Can't do this on a cage rotor design, but on the wound rotor, we can insert a resistor into the circuit and increase the rotor resistance. And this has the effect of increasing the starting torque. So if we have a very heavy load, we can add resistance to the rotor circuit in a wound rotor and get more torque. So let's look at what this would look like graphically. Suppose I'm going to graph the induced torque as a function of speed. We have this synchronous speed, and I'm going to use 3 different values, 3 different resistors. This resistance you can think of as the total rotor resistance. So I'm adding resistance to the rotor So I could have a curve that looks like this. And then I could have another one, perhaps, that looks like this. And then maybe another one that looks like this. And let's call this one R1, this one R2, and this one R3. So R1 would be greater than R2, which would be greater than R3. So when I put more and more resistance into the rotor circuit, my starting torque goes up. See, here's the point, is that when my speed is 0 with little resistance, my starting torque is here. As I add some resistance, it goes up, and then if I add more resistance, it continues to go up. And I can use this to create more torque at starting for a very heavy load. And then you could imagine what I could do is I could have this resistor that I switch in when I'm just starting the motor up and the speed is 0, and then once the load starts to move, I can switch that resistance out. Right? The disadvantage of having that resistor there is that I'm consuming more power. I'm wasting power. But I can have it in there when I need it, and then I can switch it out as the torque moves closer to the synchronous speed.